Have you ever, taken a massive document, maybe a dense 50-page legal brief or, a giant text file of your entire conversation history with a client and just dropped it into an AI prompt box?
Oh, yeah. I think we all have at this point.
Right. You hit enter and you're expecting the system to act as this, all-knowing superhuman assistant.
Exactly.
But then it spits out an answer that feels completely oblivious to a crucial detail that was hidden right there in the text.
Yeah, it completely misses the point.
And it's frustrating because we have all been marketed this idea of, infinite context windows, this promise that modern AI can just read, retain, and synthesize absolutely everything we feed it.
Right, but it really begs a mechanical question, doesn't it? Like, what is the AI actually doing with all that text?
Yes, exactly. Are these models genuinely speed reading the whole thing? Or is it more like, I don't know, asking a friend to read a 1,000-page book in 10 seconds?
Yeah, that's a great analogy, actually.
Do they actually digest it, or do they just skim the introduction, skip to the conclusion, and just, pretend they read the middle?
Well, I mean, it is a critical distinction to make, especially because we tend to anthropomorphize this technology so much.
Oh, for sure. We treat it like a person.
Right. We assume that just because the user interface allows us to paste 50 pages of text into a box without the system throwing an error code, the neural network is therefore comprehending all 50 pages with equal fidelity.
Right. It didn't break, so it must have understood it.
Exactly. But the reality of how these models process sequence and distribute their attention is just much, much messier. The mechanics of information retrieval inside a neural network are actually subject to some pretty severe limitations when the data scales up.
And that is exactly what we are getting into today. So for everyone listening, our deep dive today is built on a stack of fascinating research.
Really groundbreaking stuff.
Yeah, specifically a landmark paper from researchers at Stanford, UC Berkeley, and Samaya AI. And the paper is titled Lost in the Middle: How Language Models Use Long Contexts.
It's such a fitting title, honestly.
It really is. So our mission today is to look at the hard data of how these models actually process long context, find out where their structural blind spots are, and figure out how you can hack your own prompts to stop the AI from forgetting the most important details.
Because it will forget them.
Right. We are moving away from the theoretical marketing promises of AI memory right into the engineering reality of how it performs under pressure.
And, the testing framework they set up to measure this is incredibly revealing.
Yeah, tell us about that. How did they actually test it?
Well, to isolate how well an AI remembers different parts of a document, they designed a multi-document question answering task.
Okay.
They used the Natural Questions Open Dataset, which is essentially a massive archive of historical search queries that everyday people actually typed into Google.
Oh, wow. So real human questions.
Exactly. Paired with the specific paragraphs from Wikipedia that contain the correct answers.
Okay, let's unpack this a bit. They didn't just hand the AI a single Wikipedia article and ask it a question about it, right?
Well,
They basically turned it into a massive game of hide and seek.
precisely. They would feed the AI one document containing the correct answer, but they buried it within a pile of completely irrelevant documents.
Right, to confuse it.
Yeah, they referred to these as distractor documents.
Yeah.
And as they ran the tests, they scaled this up, giving the AI up to 30 distinct documents to process simultaneously.
30 documents all at once.
Right. And the key variable here was the position of the target information. Sometimes they force the document with the correct answer to sit at the very beginning of the prompt.
Okay.
Sometimes they place it at the absolute end.
Okay.
And sometimes they buried it right in the middle of this giant mountain of text.
So the data from that hide and seek game produced this really distinctive U-shaped performance curve, right?
It did, yeah.
Like, when the document with the target answer was placed at the very beginning of the prompt, the AI's accuracy was incredibly high.
Which is known as primacy bias.
Right, primacy bias. And then when the answer was at the very end of the prompt, like right before the question was asked, the performance shot back up again.
Yeah, recency bias.
Exactly. But when the answer was buried anywhere in the middle, the AI's performance absolutely plummeted. I mean, it entirely lost the plot.
It really did. And we need to look at the mechanics of why that happens.
Yeah. Why is it so bad at the middle?
Well, in a transformer model, which is the architecture underlying almost all modern large language models, there is a mechanism called self-attention.
Okay, self-attention.
Right. When the model processes text, it assigns a mathematical weight to every single word or token in relation to every other token.
Yeah.
It is trying to figure out which words matter most to the current context.
Right, it's drawing connections.
Exactly.
Huh.
But when you dump 30 documents into the prompt, you are stretching that attention mechanism over thousands and thousands of tokens. The mathematical weights just get diluted.
Ah, I see.
So the model naturally anchors to the absolute boundaries of the text, the very first tokens it processed and the most recent tokens it processed.
Because those are the easiest to grab onto.
Yes, because those boundaries provide the strongest structural signals. So the middle essentially becomes a blur of diluted attention.
Wow. And, it is the sheer magnitude of that degradation that really stands out in the data for me.
Oh, the numbers are wild.
Yeah, like to get a baseline, they benchmarked these models by asking them the questions closed book,
Right.
which means they gave the AI 0 documents, no Wikipedia text at all, and just asked the question to see if the AI could guess the answer purely from its internal training data.
It's just from memory.
Exactly. And for the model GPT-3.5-Turbo, its closed-book accuracy was 56.1%.
Okay, so it gets it right a little more than half the time on its own.
Right. But when they provided the actual text containing the correct answer and placed that text in the middle of 20 or 30 distractor documents, let me make sure I have this right. The AI's accuracy dropped below that 56.1% baseline.
Yes. Providing the actual answer actively degraded the model's ability to reason.
Wait, so giving the AI the actual text with the answer made it dumber than if it had just guessed from its own internal memory?
Yes.
It's like bringing an open textbook to a test, getting overwhelmed by all the pages, and scoring worse than if you just winged it.
That is exactly what's happening. The sheer volume of irrelevant context overwhelmed the attention heads. It forced the model to divide its processing power across so many distractor tokens that it actually lost access to its own internal baseline knowledge.
That is insane. The added context literally becomes a liability.
It does, and this creates a significant problem for anyone using these tools to summarize research or, analyze legal contracts.
Because those documents are huge.
Huge and full of complex human language, nuance, semantics, varied sentence structures. So the natural hypothesis from an engineering standpoint is to question whether the complexity of natural language itself is the confounding variable.
Like, is the AI failing because human grammar is just too messy to parse at scale?
Right. So to test that, the study stripped away all the semantics. They designed a synthetic key-value retrieval task.
Okay, how does that work?
Well, they removed all sentences, paragraphs, and facts. Instead, they fed the AI a JSON object filled with random 128-bit UEADs.
Okay, for anyone who doesn't spend their days looking at code, a JSON object is essentially just a highly structured digital filing cabinet.
Right.
And a UUID is a long, unique string of random numbers and letters, like a serial number, right?
Exactly. It has zero linguistic meaning, no grammar, no context, no narrative flow whatsoever.
So it's just pure data.
Pure data. They presented the AI with a massive list of these random alphanumeric pairs and asked it to retrieve the specific value associated with one specific key. It is the purest, most mechanical data matching task possible. There is no reasoning required, just raw pattern recognition.
Yet, despite removing all the confusing human language, many of the leading models at the time, like MPT-30B and standard GPT-3.5, they still exhibited that exact same U-shaped failure curve.
They really did.
When tasked with retrieving a key from the middle of a massive list of 140 or 300 pairs, the middle was still a completely black hole.
Yeah, the data just got lost.
Now, the data did show that Claude-1.3 and its 100K variant were the exceptions here, performing near perfectly on this specific pure data task.
Right. Claude handled the UVIBs well.
But for the others, the structural blind spot persisted even without language to confuse it.
And that proves the lost in the middle phenomenon is deeply architectural. It is a limitation of how sequence is processed, not just an inability to parse human grammar.
Right.
But, this synthetic data test also exposed a harsh reality about how these tools are marketed. The study specifically evaluated extended context models.
Oh, right.
These are the versions heavily advertised by AI companies as the ultimate solution for processing massive documents, like the 16K version of GPT 3.5 Turbo.
Here's where it gets really interesting to me. You see the marketing pushing 16K or 100K extended context models, implying that the AI is now smart enough to read an entire novel at once.
Right.
But when they tested these extended models on 10 to 20 documents, their performance curves almost identically overlapped with their standard shorter context counterparts.
Yeah, they didn't do any better at finding the middle.
The middle of the curve dipped just as low. Hold on. AI companies explicitly market these extended context models as the solution to reading long documents. But you're telling me that just because they have a bigger mouth to swallow more tokens, it doesn't mean they actually digest the middle any better than the standard models.
That is exactly what the data shows. Having an extended context window does not equate to extended comprehension. From a software perspective, a massive context window simply means the system has a larger buffer. It won't crash or throw a token limit error when you paste a massive file into it.
So giving the AI a 100K context window is basically like giving an office worker a massive 20-foot long desk.
Yeah, exactly.
Sure, they can physically fit 100 open books on that desk without any of them falling on the floor, but they still only have two eyes. Just because the desk is wider doesn't mean their brain can simultaneously read and synthesize the books sitting right in the middle of that desk any better than they could before.
That's a perfect way to put it. The architecture prevents a buffer overflow, but it guarantees absolutely nothing about the model's ability to pinpoint and effectively use that information once it is ingested.
Right.
It is purely a capacity upgrade, which really forces us to look closer at the underlying architecture to see if there is, like, a mechanical fix for this.
Yeah. Can we fix the desk?
Well, the study compared the two dominant structural approaches in the field. You have decoder-only models, like the GPT series and Llama, versus encoder-decoder models, like Flying UL2 and Flan 25XXL.
Okay, this requires a bit of technical grounding for us. A decoder-only model is autoregressive, right?
Correct.
So when it generates text, it only looks backward at the previous tokens to predict the next one. It is essentially a one-way street.
Yes, but an encoder-decoder model uses a bidirectional encoder,
Meaning it goes both ways.
meaning it processes the input sequence in both directions simultaneously before it starts generating an answer. It evaluates each document in the context of what comes before it and what comes after it within the sequence.
Okay, that makes sense.
Because the attention mechanism can look forward and backward across the entire prompt before committing to an output, these encoder-decoder models are surprisingly robust against this middle blindness. The U-shaped curve flattens out significantly.
Wait, if bidirectional encoding fixes the blind spot, why aren't all the major AI labs just using encoder-decoder architectures for everything? What is the trade-off here?
Well, the trade-off is computational efficiency and a strict limitation on sequence length.
Okay.
The bidirectional encoder only avoids the U-shaped curve when the text you feed it falls within the exact sequence length it was exposed to during its training phase.
Oh, I see.
So if an encoder-decoder was trained on a strict limit of 2048 tokens, its bidirectional attention is optimized for that specific length.
Right.
The moment you push past that training length, say, by feeding it 4,000 tokens, the mathematical weights break down, and that dreaded U-shaped curve immediately reappears.
Wow.
And you cannot dynamically scale an encoder-decoder to handle massive new context windows without retraining the entire model from scratch, which is incredibly expensive.
Okay, so changing the architecture isn't a quick fix. What about changing how we prompt the AI? We always hear about prompt engineering as this secret weapon.
Right, prompt hacking.
Yeah. The study tested a technique called query-aware contextualization. Essentially, they placed the query, the specific question they wanted, answered both at the very top of the prompt before the documents, and then repeated it immediately after the documents right at the bottom.
And the outcomes of that prompting technique revealed a massive divide in how AI processes different types of information.
Really?
Yeah. When they applied that before and after query trick to the synthetic UUID task, the one with the random serial numbers, it drastically improved performance. It pushed almost all the models up to near-perfect scores, even for the data buried in the middle.
So query-aware contextualization is like a teacher giving you the exact test question before you read a dense chapter, and then repeating that exact same question immediately after you finish reading.
Exactly.
It primes your brain on exactly what to look for. But why does that prime the AI perfectly for memorizing a random string of alphanumeric code while doing almost nothing to help it answer a multi-document question about Wikipedia articles?
This raises an important question, and it really comes down to the fundamental difference between pattern matching and semantic reasoning.
Okay.
Finding a precise string of random characters, like a UUID, is essentially a Ctrl-F search function. When you place the query before and after the data, you create two incredibly strong mathematical anchors.
Right.
The attention heads can easily bridge those anchors to find a perfectly matching string of characters anywhere in the text. But reading 20 different Wikipedia articles to synthesize a semantic answer requires holding on to abstract concepts.
That's way harder.
It requires cross-referencing ideas. The AI has to weigh the importance of a sentence in document 4 against a conflicting sentence in document 19. A prompt trick cannot magically grant the model the sustained long-range reasoning required to synthesize meaning across 30,000 tokens.
Which brings up how these models are fine-tuned to interact with us. I know the study specifically looked at instruction fine-tuning.
Yes, they did.
They compared a raw base model, MPT-30B, to its instruction-tuned counterpart, MPT-30B Instruct. And instruction tuning is the post-training process that takes a raw text predictor and turns it into a helpful chatbot that actually listens to your commands.
Right, and a very reasonable hypothesis in the AI community was that instruction tuning causes the primacy bias.
Oh, because we train these chatbots to pay hyper-close attention to the system instructions, right?
Exactly. And those instructions are almost always placed at the very top of the prompt. So the theory was that the model learns to overweight the beginning of any text it reads.
That makes total sense.
But the data disproved that. Both the raw base model and the instruction-tuned model exhibited the exact same U-shaped failure curve.
So the blind spot is not an artifact of how we train them to behave like chatbots at all.
No, it is an inherent characteristic of the base neural network.
Okay, so if architecture has strict limits, prompting tricks only work for basic searches, and chatbot training isn't to blame, what if we just throw raw computing power at the problem?
Just muscle through it.
Right. Do the massive multi-billion parameter models just muscle their way through the middle blind spot? I mean, they tested this by analyzing the Llama 2 family of models, moving from the smaller 7 billion parameter version up to the massive 7 billion parameter version.
And the scaling behavior was highly counterintuitive.
How so?
The smallest model, the 7 billion parameter version, didn't actually have a U-shaped curve. It only had recency bias.
Wait, really?
Yeah, it entirely ignored the beginning and the middle and only remembered the last few paragraphs it processed.
So it just lacked the internal complexity to hold on to the start of the prompt, but when they scaled up to the 13 billion and 70 billion parameter models, the full U-shape emerged.
Exactly. As the parameter count increases, the model develops more sophisticated attention heads. It gains the capacity to evaluate those early structural anchors, resulting in that high primacy bias.
Right.
But the core degradation in the middle remains completely unsolved. Adding billions of parameters makes the model smarter at the boundaries, but it does not cure the mid-document amnesia.
Wow. So what does this actually mean for you when you're sitting at your computer trying to get work done? This structural flaw heavily impacts how enterprise AI tools are built right now.
Oh, absolutely.
Most modern AI search engines and corporate chatbots rely on a framework called Retrieval Augmented Generation, or RAG.
Right, are good blinds.
It is a retriever-reader setup. You ask a question, the system queries a massive vector database, retrieves a bunch of relevant text chunks, invisibly pastes them into your prompt, and then the language model reads them to generate your answer.
And to test the real-world implications of these RAG pipelines, the study simulated an open-domain question-answering environment.
Okay.
They started by feeding the AI the top 20 retrieved documents to answer a question. Then they increased the payload to the top 50 retrieved documents. The prevailing logic in software development is that giving the model more contextual data will yield a more accurate, comprehensive answer.
Right, more data is better. But the performance saturated incredibly quickly.
It did.
It flatlined long before the search engine ran out of highly relevant documents. Pushing the context window from 20 documents up to 50 documents provided a microscopic 1 to 1.5% improvement in accuracy for flagship models like Claude and GPT.
Just 1%. And that tiny fraction of a percent comes with a massive operational cost.
Because tokens aren't free.
Exactly.
Yeah.
Every token you feed into a language model requires compute. Adding 30 extra documents drastically increases the latency, the actual seconds you sit there waiting for the answer to generate.
Yeah, no one likes staring at a loading screen.
And it also spikes the API costs for the developer. You are forcing the system to burn significantly more time and money to process a mountain of text. But because the attention mechanism dilutes and loses the middle anyway, all that extra computation barely moves the needle on output quality.
It is a terrible return on investment. So if you are personally curating research for an AI to analyze, the takeaway is clear. Do not just dump a giant, unorganized folder of PDFs onto its digital desk.
No, don't do that.
You have to be a brutal editor of your own prompts. If you read through a document and you know for a fact that two specific paragraphs are absolutely critical to the analysis you need, you should physically copy and paste those paragraphs to the very bottom of your prompt.
Yes.
Force them to be the very last tokens the AI processes before it generates a response.
The empirical data fully validates that strategy. The researchers advocate for techniques like ranked list truncation. That simply means deliberately restricting the number of documents you pass to the AI.
Cut out the noise.
Cut out the noise, exactly. They also emphasize re-ranking, which is the programmatic version of what you just described, forcing the most vital, high-density information to the extreme top or the extreme bottom of the context window.
Right.
We're currently living in an era where everyone is hyper-focused on AI generation capabilities. But this research proves that human curation is equally, if not more, vital. Precise context will always outperform massive context.
Be a brutal editor. I love that. Now, I want to shift the focus for a moment as we wrap up, because the outro to this paper touches on something far beyond token limits and vector databases.
It's really philosophical.
It does. The researchers pointed out a profound parallel between this mechanical AI failure and the nature of intelligence itself. This specific U-shaped performance curve, where the subject remembers the beginning, remembers the end, but completely loses the middle, is not a new phenomenon. It actually has a deeply rooted name in human psychology.
It does. It is known as the serial position effect.
Right.
The foundational research on this was conducted by the German psychologist Hermann Ebbinghaus way back in 1913, and it was later expanded upon by Bennett B. Murdoch Jr. in 1962.
Yep.
Ebbinghaus ran experiments where he asked human subjects to recall a free association list of items or words.
Okay.
The results consistently showed that humans distinctly remember the first items they were exposed to, which Ebbinghaus defined as primacy, and the very last items they heard, which is recency. But the items in the middle of the list undergo massive cognitive decay. They get entirely lost.
Which is the exact same structural amnesia we are seeing in state-of-the-art artificial intelligence.
If we connect this to the bigger picture, the irony is really profound. The core engine of a language model, the transformer self-attention mechanism, operates on pure mathematics.
Right, it's just numbers.
Mathematically speaking, the self-attention mechanism is perfectly capable of calculating the weight and retrieving any token from its context window with equal precision. Unlike a biological brain dealing with fatigue or, chemical limits, there is no physical hardware reason. A neural network shouldn't have perfect, flawless recall across an entire document.
Yeah, it shouldn't get tired.
Exactly. Yet, despite being a mathematically pristine retriever, when scaled up, it degrades into the exact same flawed pattern as a human brain.
It is wild to think about. You upload a massive text file expecting the cold, calculating perfection of an all-knowing machine.
And what do you get?
You get a system that essentially crams for a midterm exam, gets overwhelmed by the reading material, and forgets the middle chapters just like we do.
It really forces us to ask whether we are simply engineering around a software bug, or if we are observing a universal property of complex systems trying to balance massive amounts of input.
And that is a lingering thought to leave you with as these context windows get pushed to 1 million, 2 million tokens and beyond. If we are engineering these massive, mathematically perfect systems, but they inevitably manifest the exact same cognitive bottlenecks and memory blind spots as human beings, are we uncovering a fundamental limit to how information itself can be processed in this universe? Or in our race to build artificial intelligence, did we just accidentally teach our machines to be a little too human?